Okay, so we introduced two parameters in thermodynamics here. One of them is called delta G. Okay, well, this is called Gibbs free energy. Okay, so this Gibbs free energy will tell us whether the reaction will move forward to products, favor products, or not favor products. So it takes input from enthalpy, so this is enthalpic contribution and entropic contribution. And the temperature also plays a role whether the reaction will go to products or not. All right, so this can happen at standard state. So standard state basically means you put that symbol in there, not. This is called the not symbol. Okay. Or it could happen under non-standard state conditions. Okay. Any temperature and any pressure. So we talked a little bit about entropy here, delta S, and we talked about it being a measure of disorder. So if we go to page 2 of our notes, okay, all of these things are representative of disorder. Okay, so solid is generally considered very ordered, liquid is generally considered in the middle, and then gas is highly disordered. So this would be an increase in positivity. Okay, S, sometimes it can be change of S. So S is the only thermodynamic variable that can have a standalone. Because usually it's delta H, the change in enthalpy, and delta G, change in Gibbs free energy. But S can be that or delta S. And you can see here all of these things. So you can look on this slide here or this notes. Okay, all of these things are positively associated with entropy. Okay, so all of these transitions, all of these reactions, solid to a liquid, liquid to a vapor. Okay, adding solute to a solvent. Okay, all these phenomena increase disorder. Disorder, which means their S will be positive, or the change in S will be positive. All right, other things that increase disorder. So I've written a paragraph here. Anything that involves motion, vibrational, translational, more degrees of freedom. Your book, if you read the textbook, not only the PDF textbook, the free PDF textbook, but the one that I scanned, which was what this was based off of. Okay, anything that has more microstates. Okay, all of these are positive entropic contributions. Okay, usually I should also mention more mass, more atoms. Anything where there's more. Okay. Higher temperature. Okay, I want you to associate all of these with greater entropy. Okay, more positive S or more positive delta S, S or delta S. So we also have standard entropy. Okay, so standard entropy just basically means standard state. Okay, so anytime you see that not symbol, okay, that means standard state. Standard state conditions. So let's go to page 3. So, and basically, what I'm trying to say is that entropy means disorder. Okay, that's all it's trying to say. Disorder. let's do some example problems. So we actually have some values here. Okay, so we got some values. This is not for you to memorize. So, anytime you see these tables, you don't memorize them. But I don't know if you remember this, but from Gen Chem 1, there is a change in enthalpy, or the enthalpy of a reaction, which is sum of the products of products minus reactants. So it's the same thing here. So you'll use a lookup table. You look up these values here on the table, and then you'd sum up the products and you'd sum up the reactants. This is what we learned in Gen Chem 1. We continue the same. Okay, this is looking at the change in entropy. Okay, this sigma means sum. Signs mean something here in thermodynamics. So if it's a positive sign, that means there's more disorder. Okay, more disorder. Okay, the negative sign for the delta S change in entropy means there is more order. Okay, something that is more order is something also termed non-spontaneous. And when your delta S is positive and there's more disorder, there's increase in entropy, this is called spontaneous. Okay, remember the kitchen sink example we talked about before. So let's do some problems here. All right, predict the entropy change from the following processes. Would it be positive or negative? Okay, would this be increase in order or an increase in disorder? Condensing water vapor. Okay, condensing water vapor. Condensing water vapor is water going from a gas to a liquid, so we predict the delta S would be negative. Okay, right? Liquid to a gas is evaporation. The back process is called condensation. So that is more this gas to a liquid. Yes, that is more order, so that would be negative. How about forming sucrose crystals from a supersaturated solution? Forming crystals, what do you think that is? Okay, more order, okay. So I don't know if you guys remember a lab we did on the density of solids. Do you remember that lab, density of solids? So there they mentioned that each of those metals that you weighed and figured the density of, they composed of unit cells. A crystal is also composed of individual units called unit cells. So crystals are very ordered. Okay, some are more ordered than others, and the way the crystals are ordered is used by X-ray crystallography to get the structure of DNA. Remember Rosalind Franklin and her X-ray diffraction? Well, they did it on DNA crystals. So you need to crystallize the DNA or crystallize the proteins. So the point is crystals are very, very ordered structures. And if you're forming a crystal, okay, sugar crystals or protein crystals or DNA crystal, that is something that's very, very ordered. So you're going from disorder to order, and delta S would be negative. Same thing, more order. Heating hydrogen gas from 60 degrees to 80 degrees. When you heat something, what do you think happens? Do you think that's more order or more disorder? More disorder, that's correct. So more disorder we associate with spontaneous processes. That also means our delta S is going to be positive. and sublimation of dry ice. Okay, what's sublimation? Okay, it's a solid that skips the liquid step and goes to a gas or a vapor. So solid to a gas. Is that right? Solid to a gas, I think that is, yes. So gas is very disordered. They're all roaming around, floating around. You can't get them ordered. So the delta S for this phenomenon will be positive as well, more disorder. So that's how we do these types of problems. Okay. Go to page 4 here. All right, how about going from I2 solid to 2 moles of I2 gas? Okay, what would we predict the entropy change would be?
Positive.
Yes, very good, positive. Okay, so when we do this equation, here, where's that equation? Well, yeah, when we do this equation and put in these numbers in for these values, for these elements, we would expect that number to be positive. All right, 2 zinc solid. Okay, 2 zinc solid plus O2 gas goes to 2 zinc solid. Okay, so we have 3 moles, 2 moles of the solid, 1 mole of the gas, going to 2 moles of solid. So ultimately we're going from 3 to 2, so that's more order. And not only that, we're making a solid. Okay, so what do you think the change in entropy for that will be? Positive or negative? Okay, the answer would be negative. Okay.
So it goes off the moles too, so if we're forming like new things, like decreasing the number of moles, that's also more order.
Yeah, as opposed to like increasing. Let's say you're going from 3 moles to 5 moles. There's more stuff, more things, more motion, more can happen. Yeah, so this would be delta S would be negative. Okay. This is not, I will not ask you this on the exam, but you have 1 mole of a gas plus 1 mole of a gas going to 2 moles of a gas. And 2 moles of a gas are going to 2 moles of a gas. So here the entropy change would be neither positive or negative. So there's no change in entropy. Do you see that? Because you have 1 mole of a gas plus 1 mole of gas is equal to 2 moles of a gas going to 2 moles of another gas. It's like they're joining together, and it's neither positive or negative.
So is it always like that, where the moles of the reactant reflect the state of the product? Or?
You have to balance the equation. So when you balance the equation, there's no number here, so that's 1. There's no number here, that's 1, that's 2. And here it's 2. So 2 gases, 1 plus 1 is going to 2 gases. So it's not increasing the number of gases, but it's not decreasing the number of gases. You're not making a solid, you're not making a liquid. So yeah.
So it's like the amount changes, then the state changes. Like if there was 1 more oxygen gas
In the product,
in the reactant.
if there was 1, if it, like 2, if there was
For
2. Yeah, if there was 2 and it's balanced, if you put a 2 here, it won't be balanced. But let's say there was a 2 here and it's still balanced, then you would have 3 gases going to 2 gases, then the delta S would be negative. As long as it's balanced. So you always want to make sure you balance your equations. All right, so we also have for a spontaneous process, the delta S of the system plus the delta S of the surroundings will be positive if it's at equilibrium. Okay, they're equal to 0. And then I just went over the standard entropy of the reaction. Okay, just know that this is at standard state. see your notes for a second. Maybe Allison. Let's see your notes. I think I got an old set of notes. Look at this, so nice. Oh, yeah. Okay. Looking for a table here.
Oh, yeah.
Oh, yeah, missing table, page 6. Okay. If you give me these values at the table on page 6, we'll complete page 4. We'll complete this last set of problems, and then we'll call it a day. So I just need you to blurt out these numbers. Okay. Is that a deal? No? Let's have a punch my class. You won't. I know you won't. Okay, so let's do this problem here. All right, we're going to utilize this equation. All right, sum of the products minus sum of the reactants. So calculate the standard entropy change for the following reactions. We'll just do A, B, and C, and then we'll call it a day. All right, so sum of the products minus sum of the reactants. We're going to utilize this equation for here. By the way, what would we predict? Would we predict this prediction? Okay, would we predict this delta S to be positive or negative? 2 plus 1, 3 gases going to 2 gases, so positive, negative. Okay, let's see if it's negative or not. So sum of the products. So what is CO2 gas, Allison, from our table?
Well, just for CO is 197.
CO2 products, sum of the
it is 2, sorry.
Products.
13.8.
Okay, sum of the products minus sum of the reactants. So the products is CO2, so 213.8. That's for 1 mole. How many moles do we have? Multiply this by 2. What are the units, by the way? Joule over Kelvin mole? Joules over Kelvin. All right, thank you. Okay, so that is... okay, we only got one product here. Okay, and we multiplied it by 2. Why did we multiply it by 2? There's 2 moles. Okay, then I want you to put a big bracket after the minus sign. So here's our minus sign. Put a big bracket. Okay, sum of the products minus the sum of the reactants. So now we'll do the reactants. What is CO gas, Allison? 197.7 joules over Kelvin mole, but that's for 1 mole. How many moles do we have? So do you agree to multiply this by 2? Okay. Plus, what is O2 gas?
205.0.
Okay, so we're using the lookup table. Okay, use the lookup table to get the standard entropy values for each of these elements. What is it again, Allison?
205.03.
Okay, and we multiply it by 1. Okay, this is balanced, right? 2C, 2 plus 2 is 4. Yeah, this is balanced. Okay. All right, so we're just utilizing this equation and doing plug and play. We are predicting based on the states that this is going to be negative, and let's in fact see if this is indeed negative. So we'll do this on our calculator. Another thing is be careful. You can make a mistake on just calculator, which something I can do as well. Right, 2 times 213.8. So I definitely need someone to minus 2 times 197.7. Plus 205.03. Oh, I'm sorry, minus 205.03. I did it wrong. 2 times 213.8. So you have to distribute this negative. Okay, this negative is a train and it plows through. Okay, 2 times 213.8 minus 2 times 197.7. Okay, minus, remember this minus distributes, minus 205.03. Yeah, minus 172.8 joules over mole Kelvin. And you were right, Michael, you predicted negative, and the actual value is negative, more specifically minus 172.8 joules over Kelvin mole. So our prediction is correct. All right, let's do B and C here really quickly. Okay, what would you predict for this one here? Okay, so we have 3 moles of gas going to 2 moles of gas. You predict negative. So our prediction is delta S will be negative. Let's go ahead and do that. What is O3, Allison? Is it there? O3 gas?
Is it? See it?
Isn't it 205.03?
Is it on the next page?
Oh, 03.
I'll get it out here. Right, so we're going to utilize this equation here, and we use sum of the products minus sum of the reactants. And let me get those values for you here, just a second. Okay, I got it here, sorry about that. Okay, I got O3 being 238.82 joules over Kelvin mole. Okay, there we go. All right, so now we should be able to solve this. We predict this to be negative, right? So let's see if this is indeed negative. So we're going to take this value, and what should we multiply this by? 2. Why should we multiply it by 2? Okay, we have sum of the products minus sum of the reactants. I want you to put a big bracket there. And O2, what is O2? 205.03, and we're going to multiply that by 3. Alright, so let's see, we predict this to be negative, and let's do 2 times 238.82 equals that minus, okay, distribute that minus sign, minus parentheses 3 times 205.03, close the parentheses. It is negative, minus 137.4 or minus 137.5 joules over mole Kelvin. Okay. All right. All right, we'll do one more, and then we will hopefully have a good weekend. All right, we have one more problem here. Where did it go? Okay, there it is. All right, so let's see if this is positive or negative. You have a solid, 2 solid, okay, and it's going to make 1 solid plus 1 liquid plus 1 gas. What do you think the delta S would be, positive or negative? Okay, definitely positive. All right, I think so too. This is our prediction. Let's go ahead and see what that's going to be. So sum of the products minus sum of the reactants. Sum of the products minus sum of the reactants. So I got Na2CO3 being 135.98.
It has it right there. Oh, I don't know.
Yeah. On my notes, it says 138.79. Right? Yeah.
No.
Oh,
It's like right below the problem.
ours has.
Oh, not in, this isn't. Yeah. So what do you have for Na2CO3? 138.79. Okay. Is this balanced? 2Na, 2Na, 2CO3, 2 carbons, 2 carbons, and 2 H's, 2 H's, 2, 3 hydrogen, 6.
Yeah.
6. It's balanced, yeah. Okay. So Na2CO3, you got it as 138.79. Okay, so we will multiply that by 1. Okay, and H2O liquid, 69.91. Okay, this is for H2O. Okay, sum of the products minus sum of the reactants. Okay, plus CO2 gas,
213.8.
213.68.
0.8.
0.8, okay. Okay, so those are the products. Okay, I want you to put a minus sign in a big bracket and the reactants. So sodium bicarbonate, 102.09.
Ours is 101.7.
101.7, okay. And what do we need to multiply that by? 2 times 101.7. Okay. Okay, 101, 102, that's fine. Minus 102. All right, so this is the math, and we're going to see if it is indeed positive, okay? So 138.79 plus 69.91 plus 213.8 minus, let's put this in parentheses, minus 2 times 101.7, close those parentheses, 219.1, and we predicted it to be positive, and it is positive. Okay. So, yeah. So, and we predicted it to be positive, the actual number is positive, and this is a reaction that's producing more disorder. A solid going to a gas, 2 solids going to a liquid gas, and another solid. Okay, that's just more entropy that's being made in the system.